Hello everyone, welcome back to our part 2 of the piezoelectric energy conversion. I hope you have reviewed the material I delivered in the part 1 of the piezoelectric energy conversion. It's an exciting topic because piezoelectric is a very efficient material for energy conversion. The material I delivered is based on several journal papers. You are encouraged to download the journal papers and read it by yourself. Most importantly, you need to derive the equations and generate the figures by yourself. This way, it can help you to really understand what's going on there. Otherwise, you will forget everything soon. Then it won't leave a trace in your mind. Okay, now let's move to the part 2 of the piezoelectric energy conversion. We have a device shown in the slide. It's a bean, but it looks like a little bit weird because it's not straight. It's going like meandering. And this end is fixed. And it goes like a serpentine. So it could go on like 1, 2, 3 till n segments. Why did I do this? You know, to conversion the mechanical energy in the ambient environment, usually the frequency is low. It might be lower than 100 Hertz, but micro device is very small. Remember, we are talking about micro device in this series of energy conversion device. For small micro device, because it's very small, so the resonance frequency usually, is in the kHz range or even megahertz range. Then the traditional micro devices are not suitable to convert the low frequency environmental vibrations. So we need to decrease the resonant frequency of the micro device. One way to do that is to create a beam like this, a meandering beam with several segments. Then it has multiple vibration modes near the low frequency range, which is suitable for us in our applications. So in this case, if there's a vibration in the Z direction, this is X, this is Y. So if there's a vibration in the Z direction, these segments is going to bend and also twisting. So twisting plus bending, we have a lot of exciting things going on in the structure. And in this figure, the piezoelectric material, we have the piezoelectric layer and attached, bonded to the substructure layer. So we call this unimorph, like we have a single layer of piezoelectric layer. Then if there's a vibration in the Z direction, the mechanical energy is going to generate stress inside the piezoelectric material. Remember, we have charge density equal to dielectric constant multiplied by electric field plus those piezoelectric coefficients multiplied by stress. So, we have stress, then we could generate charge, the electric displacement or charge density on the electrodes, which is good. So that we can take those as the current. See, these sentences just explain if there's a bending here and also twisting, it's going to create the angle, the angular displacement and linear displacement to the second segment. Then it just keep going on. We just accumulate those linear displacement and angular displacements. Then we are going to create very versatile vibration mode near the low frequency range to help us to convert the low frequency vibration energy into the electrical energy. And this schematic explains what's going on for a single beam structure. And the vibration is in the z direction. Then the beam just bending. Bending dominates in the mechanical behavior of the device. But what if we have like 1, 2, 3, we have 3 segments. The first segment, we have not only bending, but also we have twisting because there's a torque applied to this beam segment. And the same, we have bending and twisting in the second segment, and bending and twisting in the third segment. Then we are going to create a very versatile, very, a bit complicated vibration mode in the structure. The complicated vibration mode will have a large stress accumulated in the structure to generate electrical energy. Okay, to create a mathematical model is important. Not only it helps us to understand the behavior of the device, also it can help us to design or optimal design for a better device. And this equation derived the equivalent bending stiffness yi. Y you can take as the Young's modulus. I is the second moment of inertia. So this is the equivalent bending stiffness because it's a multiple layer structure, a composite structure. And the parameters are listed here. If you are interested, you are encouraged to go to this reference, number 7, to find out how to derive this expression to simulate the bending behavior of the structure. And this one is the equation of motion. So this one for static motion and this one for dynamic motion. So this, you could think this one is a mass acceleration term and this one is the strain energy term. So rho A is the mass per unit length of the beam. And in order to solve this equation of motion, we could use the separation of variables. We can assume the solution can be separated into capital W of x, eta of t. Then the solution W of x can be taken as this exponential form, cosine sine form. Then exert this expression into the equation of motion, we can get the vibration, the frequency, the characteristic values of this equation. And this one for torsion motion. And this is the equivalent torsional rigidity. And to solve this equation of motion for the torsion, we could we could use separation of variables and assume the solution form here, and to solve the characteristic equation and get the characteristic values, the eigenvalues, which is the resonance frequency of the device. Remember, we had said we have n beams. Then we have a lot of equations. Then we need to have the same number of equations to solve for the same number of variables. So for each beam, we have 6 boundary conditions for the two ends of the beam. And since we have 6 unknowns for each beam, so we have 6n equations, unknowns. So we need 6 multiplied by n conditions to solve for the system of equations. So each beam we have 6 boundary conditions. Then we can have the equilibrium equation and the continuity equation. So total we have 6n equations to solve for the 6n unknown. So the following relations here, we have the bending moment and shear force and twist torque used to write the boundary conditions. So the boundary conditions at the ends, it could be, we can define the deflection, slope, and twist angle. And the parameters we used to solve this system of equations. Okay, so in this figure shows the x-coordinate represents number of beams. The y-coordinate represents the frequency we solved. So see, the frequency could be lower than 100 Hertz if we have for the mode 1 and the segments larger than 10. See, if we had large number of the beams, then the resonance frequency of first mode could be low. But if we use less number of members beams, then the first mode of the frequency will be higher. And this figure shows the vibration mode of the beams. So for this mode, the first mode we had 154 Hertz resonance frequency. And for this mode, we have 322 Hertz resonance frequency. See, the vibration mode is, we have a lot of vibration mode with different vibration resonance frequencies. Okay, so in this part, the authors used the formal, like let's say rigorous way to derive the equation of motion and use the very, let's say, precise, accurate boundary conditions to solve for the equation. So let's say that solution is accurate, but it takes numerical ways. It takes, say, we need to solve for more equations. And so we use more computational power to do that. But we have some approximate solutions. We call this, we can use energy method, the radius method, to solve for the equation. So for the radius method, we could assume a trial solution and use the energy formulation to solve for the resonant frequency. See, first we formulate the potential energy, the strain energy, the strain energy form. Also, we formulate the kinetic energy, of the tip and each segment in the length direction, length from S equals 0 to L. And for each segment, we have mass and the velocity. For the tip mass, we have the velocity. Okay. Then we could use the energy method to derive the natural frequency here. So, say we need a trial function to solve for the to use radius method to solve for the solution. So usually we use the static deflection shape under gravity as a trial function. So, see, we can use gravity as the forcing term and solve for the static deflection shape due to the gravity. And the result is quite good. For the lowest mode, use the radius method is almost the same as the exact solution. Okay, we prove that radius method is quite efficient. And usually we use the static deflection solution as a trial function. It's quite convenient and, let's say, accurate in this case. So after we did the numerical analysis, the modeling, and now we need to carry out the experiments to compare, to demonstrate the efficiency of the piezoelectric energy conversion device. And also we'd like to know the accuracy of the analytical solutions. To do that, we compare the solutions of those equations with the experimental results. Okay, these figures shows the, say, frequency response for various terms, the vibration amplitude. The experimental results are quite close to the model predictions. This demonstrates the validity of the analytical solutions predicted by their models. Okay, so now we finished that section. Now we are going to move to another case of the piezoelectric energy conversion device. in this case, they use a different, more efficient, but more expensive piezoelectric materials, PMNPT. Traditionally, the popular PZT material, piezoelectric material is, say, PZT, PBZrTiO3, lead, diconate, titanate material, PZT, is a traditional popular piezoelectric material. But scientists or engineers try to find out a new material with higher piezoelectric coefficient to increase the energy conversion efficiency. So they found this material, PMNPT. It has fourfold increase in the piezoelectric coefficient, which is good. But because it's not that it's not used a lot, so it's relatively new, still in the development stage. So the cost is quite high. That's the disadvantage of this material. Now let's continue this mains piezoelectric harvester with the new piezoelectric material, PMNPT. See, this new material, we have lead, magnesium, niobate, lead, titanate. Is this crystal, the chemical structure formula is listed here. So this material has high piezoelectric coefficient and large electric mechanical coupling coefficient and high dielectric constants and low dielectric losses. Perfect, right? So yeah, its piezoelectric coefficient is higher than PZT. So it can improve the bandwidth, sensitivity, and the source level. So it's a much better material. And in this case, they use the D33 mode for energy conversion. The previous case used the 3-1 mode, the bending mode, and this case is different. So during fabrication, because they use the silicon wafer, and we have silicon dioxide. For PMPT, to form a composite with the silicon and silicon dioxide, the adhesion between PMPT and silicon dioxide is not good. So we need an interface layer. So the interface layer, they used ZrO2. So it has good adhesion between the silicon dioxide and the PMPT. Okay, so this is the layout of the device. And the pad are located at the edge of the device. So in this way, you can minimize the wire bonding. So wire bonding just go out. So it's relatively easier for wire bonding design. So this figure shows the fabrication steps. We have silicon dioxide, and silicon nitride, and silicon dioxide. So on top of silicon dioxide, we grow ZrO2, the adhesion layer. Then we deposit PMPT. Then we deposit chromium, then gold. As gold is the electrode material, and chromium is also an adhesion layer. Then we pattern the electrode. So in this case, we just use the top electrode, a finger type electrode on top. Then after this step, we have the etching process. Then we have the isotropic etching to release the beam, for the beam to move freely. So this is an optical microscope photo for the fabricated device. We can see the electrode. The electrodes are arranged as the finger type electrode. So this is a SEM photo of the device, scanning electron microscope photo, and it has high magnification rate, magnifications. So it's good for us to take a photo to know to see the deformation of the device. We could see the outer plane deformation due to residual stress displacement. According to the author, we have compressive residual stress in the silicon dioxide layer. So the silicon dioxide layer is near the upper part of the composite beam. So near the upper part of composite beam, we have compression. So, but in the real world, we need to have force equilibrium and moment equilibrium. So in order to reach the force equilibrium and moment equilibrium, the beam need to generate a bending moment this way. So if we have bending moment this way, means we are going to have the tension stress on near the upper part of the beam. The tension stress will balance the residual compressive stress. Then because of this bending, so the silicon dioxide has the compressive residual stress. So let's go back to the previous. Okay, so the silicon dioxide, is near the bottom part. So if we have compression here, the bending moment should go this way. So near the lower part of the beam, in order to have the tension here and compression here, so we have a bending moment this way, and the tension near the bottom will balance the compressive residual stress in the silicon dioxide layer. So this bending moment will bend the structure upward. So this is the reason we have this curling up beam. Okay, so you could see the OM photo, if we focus here, the tip is out of focus because this curling up deformation. And also, they use 100 wafer, and during the anisotropic etching, we will have the edge aligned with the 110 direction. So we designed the beam to have a 45 degree. So this way we have a large pit. So this way we could decrease the damping. So which is good. With decreased damping, we will have high quality factor. So the 100 wafer has normal direction in the 100 direction. And during the etching process, the crystalline surface, all those crystalline etching properties will create the edge along the 110 direction. Okay, so remember we have the trapezoidal beam because near the root of the beam we have large stress. So we prefer to have large device area near the root in order to convert more energy. From mechanical energy to electrical energy. Okay, so for the micro device, the PMMPT layer needs to be poured before we can use it as a energy conversion device. So this is the die containing the beams. So we have wire bonding to connect the pad to the conduction pads on the PCB board. So we also have two big wires for polling. Remember, polling requires high electric voltage. So see, the wire are large. Okay, after polling, the PZT, PMPT are ready to convert energy. So here is an experimental setup for this device. So the device is located on a vibration stage. And we have the micro system analyzer to analyze the motion of the device. And we can also use it to measure the surface profile and the vibration, the spectrum. And we need the voltage amplifier to drive the vibration stage. And they have the rectifying circuit to collect the electrical energy. And the voltage output could be monitored by the oscilloscope. And they have the resistance control box for the load resistor resistance matching. Remember, in order to have the maximum power transfer between the electrical energy and between the output of the electrical energy and the input of the resistance, we need to match the impedance of the resistor to the output impedance of the energy conversion device. So they use the resistance control box for resistance matching. Okay, so this figure shows the frequency response of the diagonal bender and the trapezoidal bender. Because the diagonal bender, it has a large pit around the device. So see, the quality factor is much higher than the quality factor of the trapezoidal bender. And the resonance frequency is also much higher than the trapezoidal. In this case, the vibration stage is built by a foam rubber. So the foam rubber as the vibration stage, it could be a low frequency filter. So it will say it's a low pass filter, sorry, not low frequency, low pass filter. So only the frequency, the high frequency cannot pass this low pass filter. So the high frequencies will be filtered out in later experiment. See, the diagonal bender has a high quality factor because it's very sharp. Remember the quality factor means the sharpness of the frequency response. And the voltage was measured by the oscilloscope. They use the rectifying circuit with 4 diodes to collect the current output. Also, they have the impedance matching to match the load resistance to the output impedance of the energy conversion device. Okay, this figure shows the resistance matching for the optimum resistance. We can have the maximum power output. But there are some problems with this top electrode arrangement. Ideally, the polling should be uniform, like this. But in reality, that's not the case. The polling has a little bit twisting near the electrode. So it's not perfect. So they have this percent polling factor, percent D33 for the not perfect condition. Okay, so now we completed the section. So we are going to discuss a new case. This new case is the piezoelectric power conversion in shoes. So we put the piezoelectric material in our shoes. While we are walking, the shoes, the piezoelectric material inside shoes will be compressed and released, compressed, released. So this compression, compression, rebound action could convert the mechanical energy into the electrical energy. So, for example, in the force displacement curve, we know if we increase the force, then this is the highest force point, and we release the force. Usually, for elastic material, it could follow this curve, come back, but for some other material, the return path may not follow the original path. So the energy stored in the system is this triangle area, and the energy returned to the system is the arc and the two straight lines enclosed area. So we have this amount of energy stored in the system for this type of FD curve. And for a sneaker sole, we could have these FD characteristics, so which is good. So in this way, we could harvest the energy enclosed by this straight line and this arc. Okay, therefore we design the sole of the shoes with a composite material. So we have plastic core at the center, and we have PVDF material, the upper part and lower part. PVDF material is also a piezoelectric material. So we have top electrode and bottom electrode to collect the power output. Then the bending action, because while we are working, we create bending in the sole of our shoes. Okay, so this is a photo of the fabricated device. So we have top electrode and bottom electrode, and this is a composite layer of the sole, the shoe sole. Okay, so this is an exploded view. So this is a PDT, piezoelectric material, and this is the sole, and we have the PVDF also. So we have PDT, one type of piezoelectric material, and PVDF, the other type of piezoelectric material. So here, because PDT is the material is relatively hard, fragile, so we put near the heel. And the PVDF is a soft material; it can be bended easily. So we put the PVDF material in the front of the sneaker. The resistor, we also need to match the resistance of the load resistor to the output impedance of the device. Okay, so this figure is the history of the voltage output. Then this is the PDT unit mole. And this one is the PVDF stave. And for the 250 k ohm load resistance. So PDT output, see, it could reach 150 volt. And for PVDF, it could reach 50 volts. And this figure is the power output versus time. So for PDT, it could have 80 milliwatt output power. For PVDF, we can have nearly 20 milliwatt power output. Okay, so we will stop here. Then the part 2 of the piezoelectric energy conversion is finished. So remember to review the course material, to download these journal papers, and you are encouraged to derive the equations by yourself and generate the figures to really understand the system behavior and to learn the material well. Okay, so I'll see you next time. Bye.